minutes after liftoff, a 14-story machine is falling out of the sky. It is moving faster than sound. Its fuel tanks are nearly empty. The ocean below offers no second chance. Then, in the final seconds, engines ignite, landing legs unfold, and the rocket touches down on a platform barely larger than itself. Today, SpaceX does this so often that the footage can look ordinary. But it is not ordinary. It is the result of one of the most violent control problems in engineering, and a decade of explosions that changed the economics of spaceflight. This is how Falcon 9 learned to come home. For most of the space age, rockets were treated as disposable hardware. Their job was to push a payload upward, separate, and disappear. Some stages burned in the atmosphere. Others sank into the ocean. Every new mission required another enormous machine. Imagine an airline throwing away its aircraft after every trip. The comparison is imperfect, but the economic problem is obvious. A rocket contains engines, tanks, electronics, plumbing, and thousands of carefully tested parts. Building all of it again places a floor under the cost of every launch. SpaceX attacked that assumption with the Falcon 9 first stage, the largest and most expensive section of the rocket. It carries 9 Merlin engines and produces more than 7 million pounds of thrust at sea level. If that stage could fly again, the company would not merely recover metal, it would recover a working launch system. The idea sounded simple: stop throwing rockets away. The physics made it brutal. After stage separation, the second stage continues toward orbit. The booster is suddenly alone, high above Earth, still moving downrange at enormous speed. It must turn around, survive re-entry, find a landing target, and erase almost all of its velocity. First, small thrusters rotate the vehicle. Depending on the mission, a boost-back burn changes its path. As the atmosphere thickens, an entry burn reduces heating and speed. 4 grid fins unfold near the top of the stage. They move through the hypersonic airflow, steering the booster toward a point on the ocean or a landing zone on shore. But guidance is only half the problem. A nearly empty Falcon 9 is so light that even 1 Merlin engine produces too much thrust for it to hover comfortably. The booster cannot pause above the deck and make corrections like a helicopter. It must ignite late, slow down continuously, and reach almost zero velocity at almost exactly zero altitude. Start too early, and the rocket can climb again or waste the fuel it needs to land. Start too late and the landing gear meets the deck before the rocket has stopped. Engineers and spaceflight fans often call this kind of maneuver a hover slam. In reality, it is a precision race between gravity, thrust, and time. And the target is moving. A drone ship rolls with the Atlantic, far beyond the coastline. Wind shifts. Sensors vibrate. Engines must restart after a trip through near vacuum and re-entry. The computer has seconds to correct errors that began hundreds of kilometers away. SpaceX did not solve this on the first attempt. Early tests ended with boosters tipping over, running out of hydraulic fluid, striking the deck too hard, or missing the ship. To viewers, each failure looked spectacular. To engineers, each one was data. The company tested legs, grid fins, engine restarts, and guidance software in real flight. A rocket would descend through cloud, appear over the ship, and sometimes vanish inside a ball of fire. The unusual part was not that rockets crashed. The unusual part was that SpaceX kept placing cameras on the target and trying again. Then came December 2015. After launching satellites to orbit, a Falcon 9 first stage returned to Cape Canaveral and landed upright. The images looked almost reversed, as if a launch were running backward. 4 months later, another booster descended onto the drone ship. Of course, I Still Love You. This time, the legs held. A landing at sea meant SpaceX could recover stages from missions that lacked enough fuel to fly all the way back to the coast. The impossible had become repeatable. Falcon 9 architecture makes that repetition possible. 9 Merlin engines are arranged in a compact pattern called the octob. During ascent, the cluster provides huge thrust. It also gives the vehicle redundancy. On some missions, Falcon 9 can complete its primary task even after an engine shuts down. During landing, the center engine becomes a control instrument. It can restart, throttle, and pivot its thrust. The grid fins handle the broad steering in the atmosphere. The engine performs the final correction. Landing legs absorb the last motion. Separate systems, operating in sequence, turn a falling cylinder into a guided vehicle. The timeline is astonishingly short. On a typical mission, the first stage shuts down a little more than 2 minutes after launch. Several minutes later, it begins its entry burn. Roughly 8 or 9 minutes after leaving the pad, it is standing on a ship at sea. Then the process changes from flight to logistics. The booster is secured, returned to port, inspected and prepared for another mission. The real breakthrough is not a single dramatic landing. It is the moment when landing stops being the end of a rocket's life and becomes one step in its operating cycle. Reuse does not make launch free. A recovered stage must be transported, checked, and refurbished. The second stage is still expended, and every mission carries labor, propellant, range, and infrastructure costs. Public price lists reveal what customers may pay, not SpaceX's private cost per flight. But the market signal is unmistakable. SpaceX can fly a high launch cadence while reusing much of the hardware. In a 2026 corporate fact sheet, the company said more than 95% of vehicle missions were reflights. A booster is no longer built for one perfect day. It is managed as part of a fleet. That fleet supports commercial satellites, national security missions, astronaut flights, and Starlink. Reuse and cadence reinforce each other. More missions create more flight data. More data can improve operations. Better operations make more missions possible. Competitors are now pursuing recoverable stages of their own. The question is no longer whether an orbital-class booster can return. The question is how quickly, cheaply, and reliably it can fly again. Falcon 9 recovers its first stage. Starship is designed around a more radical ambition. Recover both the booster and the spacecraft, then fly them again rapidly. If it works at scale, it could move far larger payloads and push reuse deeper into the launch system. But the ending has not been written. Starship remains a flight test program, and its failures are real. After Flight 12 in May 2026, the Federal Aviation Administration required another mishap investigation. Full reuse is not a finished product. It is the next engineering argument SpaceX is trying to settle with hardware. That is why Falcon 9 matters. Not because every landing is perfect, and not because rockets have become easy. It matters because a sight that once looked absurd, a booster falling tail first from space, became an operation people barely stopped to watch. The greatest change was not the flame, the landing legs, or the ship waiting in the dark Atlantic. It was the moment the impossible became routine.